In this video, we'll look at another lead code problem, which has been commonly asked in Google, Facebook, and Amazon interviews, and it's called finding the maximum subarray sum. That is, you need to find a subarray which has the maximum sum. It can have multiple solutions, that is, multiple subarrays can have same sum, but it should be one of the maximum. And what do we mean by subarray? Subarray is a part of this complete array. It can be the complete array itself, or it can be an element with just one element of the array, or it can even be empty array. So it has to be continuous, and that's the definition of subarray. Unlike subsequence, where sequence is important, relative ordering is important, but not that it should be contiguous. But in the case of subarray, it needs to be contiguous. And the job is to find a subarray whose sum is maximum. In this case, it would be this one. So you see here the sum is 4 minus 1, 2, 1, which is 6. So you cannot find any subarray whose sum is more than 6. So let's see what is the algorithm to do so. First, how many subarrays can be there? So it can start from index I and j. So start and end indices denote a subarray. And how many such pairs can be there? If this array has n elements, then it can be from 0 to 0, 0 to 1, 0 to 2, all the way up to 0 to n. Similarly, it can start from 1 also. In earlier case, starting with 0, we can have n possibilities. Starting with 1, we can have n minus 1 possibilities, because it can be from 1 to 1, 1 to 2, 1 to 3. Similarly, starting with 2, it can go from 2 to 3, 2 to 4. So n minus 2 possibility. Why we are looking in only right direction? Because if we see 2 to 1, that is already covered in the case where 1 to 2. In this case, it was already covered. And 2 to 0, this was already covered here. So every step there is one less, and this can be order n square. So you can use a brute force approach. This is the simplest solution. I equal to 0 to n minus 1, j equal to 0 to j equal to I to n minus 1. Find the sum of, this is the array A, sum of A I to j, k equal to I to j. So you are summing all the elements from ith to jth position, and then you are keeping track of maximum. So if this sum S is more than existing maximum, you update max with the new sum, and ultimately you will return max. This is a very naive solution. You are looking at all the possible subarrays, and that's why it's order n square, because there are n square subarrays. And here also you can see there are two nested loops, one from 0 to n, second from I to n. Now let's look at an improved solution, and this idea was proposed by Kadan's algorithm, and this is called Kadan's algorithm. So the main idea is that if you pick any subarray, it has to end at one of the indices, and it has to start at one of the indices. So we are moving from left to right. You can extend the same idea where you can go from right to left, but let's start from left to right. So what this idea says is that we start from leftmost element, and we keep track of two values. The best sum we have got so far, best subarray we have got so far, and the subarray ending at current index, where k denotes the current index. So initially both will be minus 2 for first index. Then when we reach at this index, this best may or may not be updated, but this has to update. So it says that current ending at the subarray ending at current index. So we have to include this current index. So this is array A and this is index K. Then SK, the best solution ending at current index, can be just AK when we find that adding the best solution, best subarray ending at the previous index, that is K minus 1, is K minus 1 plus AK. So this AK has to come. So whether or not to include the best subarray ending at previous one, that will depend on which one is greater. So if this is, let's say, less than 0, then there is no use of including this. This will deteriorate our solution. So we will pick just AK. So in this case, it will be just this one, because if we add this one, we get minus 1. If we don't, then we get 1. So this is 1. And the best solution becomes 1 because we have got a better SK. So SK is more than S. So S will be updated when we get a better solution. That is, we got a subarray ending at K whose value is more than the existing best subarray. And we keep on moving till the end, and finally we will return this S. Now why this works? Because let's say we are looking at kth index. So we have already looked till K minus 1 and we have already achieved some value of Sk minus 1. That is, we have achieved what is the best subarray that we can get, which ends at this index, one previous index. So if we add K to it, do we get a value of S which is more than the existing S or not? So we calculate Sk, the subarray ending at kth index. So let's say this was Sk minus 1. So why will this solution work? Let's say this is our final solution. That is, the subarray ends at current index K. So when we are reaching at K, what we will consider? We will consider what is the best subarray ending at previous index. In this case, it is this value. It can be any value, but we are maintaining this invariant when we are starting from left. We only include the previous solution when adding the previous plus current gives me a better solution. So we either take just the current element or Sk minus 1 plus current element. So when we reach at K, we will see what is the best subarray ending at one previous element. And we add current element to it. So we get Sk minus 1 plus AK. And we compare it with just AK and we pick the best. So this Sk, when we reach here, will achieve a value which will be equal to S. And earlier this S would be lower than this, or at least equal to it, not more than this. So whenever we get a greater value, then only we change this. So that's why it works, and it works in linear time because we are not keeping track of, we are not traversing this array twice or more than once. We are just moving once and we are keeping just two extra variables. So space is also order 1 and time is order n. So this is the time and this is space. So let's write code for this in lead code. So if there is no element in this list, then we will return 0. So if it's empty array, return 0. And then we keep track of sum max and sum including current. Then we traverse from 1 onwards, because 0 we have already taken. Or we can use this form of looping. So whatever is the sum including current, which is till the previous index. So the subarray that including the previous index plus n or n. And sum max equal to similarly max of sum max and sum including current. And finally return sum max. So it works for this condition, so we can go ahead and submit it. And we got wrong answer. Why did we get wrong answer? Okay, so this is the mistake. I am again starting from index 0. This form I cannot use. So we need to go back to our previous way of iterating. Now let's run it. Now it passes, and it's almost close to 100%, both in terms of time and memory. So this is it.